This lesson focuses on how technicians test and troubleshoot millivoltage gas control circuits using a millivolt meter. The visuals will walk through thermocouple tests, pilot stat corda checks, then thermopile systems, both 500 and 750 millivolt, using voltage drop readings at standard test points. Millivoltage circuits are powered by either a thermocouple, about 30 millivolts open circuit, or a thermopile, sometimes called a power pile, producing up to about 750 millivolts. Both are DC sources, so polarity matters when connecting a meter, especially with analog needle meters. Because it's DC, the direction of current determines needle movement. Some meters are polarity sensitive, and reversing the leads can drive the needle backward. The key habit is to verify polarity before committing to a full connection, especially on older analog meters. To avoid meter damage, the guide recommends a flash test. Clip one lead to the first test point, then momentarily touch the second lead to the other point. If the needle kicks in the correct direction, polarity is right. If it kicks backward, swap the leads before proceeding. For a thermocouple, the first check is the open circuit test, meaning no load. The thermocouple is disconnected from the pilot stat, the pilot flame heats the hot junction, and the millivolt meter is placed across the outer copper conductor and the inner conductor tip, watching polarity. A healthy thermocouple under flame should read around 30 millivolts open circuit. The material's rule of thumb is if an older thermocouple produces less than 20 millivolts, it should be replaced because it's no longer generating adequate potential. Next is the closed circuit test, done under load while the thermocouple is powering the pilot stat coil. The thermocouple is connected through a test adapter block, and the meter reads between the copper sheath and the adapter's side terminal, which is internally tied to the inner conductor. Under load, the expected reading is about 15 millivolts, roughly half the open circuit value. If that closed circuit voltage drops below 10 millivolts, the thermocouple can't sustain the coil and should be replaced. This is a classic looks fine open, fails under load situation. With the adapter in place, the pilot stat coil can be evaluated by watching voltage as the thermocouple cools after flame failure. Because current is tiny, voltage is the practical measurement. As millivolts fall, the magnetic field weakens until the pilot stat drops out and shuts off gas. Normal operation is typically 10 to 15 millivolts. The coil should hold until voltage decays to about 5 to 2 millivolts. If it drops out above 5 millivolts, the coil is weak. If it holds below 2 millivolts, the valve may be sticking. Dropout must occur within 90 seconds. For repeated pilot flame failure, the guide suggests a structured check. Install the test adapter, relight the pilot, and if needed, hold the manual reset while testing. Measure thermocouple output at operating temperature, then blow out the pilot and record the dropout voltage and the dropout time. The key decision points are if operating output is under 10 millivolts, replace the thermocouple. If the pilot stat drops out outside the 5 to 2 millivolt range, replace the coil unit. And if the dropout time doesn't meet the gas code requirement, the pilot stat assembly is the fix. Thermopile systems fail most often due to increased resistance that reduces current until gas valve coils can't operate. Common causes are loose connections, corrosion, bad splices, and excessive wire length. The most effective strategy is voltage drop testing, measuring millivolts across each component to find excessive resistance. Thermopiles come in different output classes. Around 250 millivolts is used for very simple circuits, basically a switch and a gas valve. 500 millivolts supports a gas valve plus limit and thermostat, including longer wire runs up to about 30 feet. 750 is used when control and safety circuits run in parallel. Open circuit readings are maximum, about 500 millivolts or 750 millivolts, because there's effectively infinite resistance and no current flow, like static pressure in a pipe with no flow. Once the circuit closes and current flows, the measured voltage drops. That lower value is the closed circuit reading, and it's always less than open circuit. A big idea here is source or internal resistance. It can't be measured directly, but its voltage drop shows up when current flows. In the example, a thermopile reads 500 millivolts open circuit, but only 185 millivolts closed circuit. The remaining 315 millivolts is effectively dropped inside the thermopile due to internal resistance. Interestingly, adding series resistance in the external circuit, like a heat anticipator, reduces current. With less current through the thermopile's internal resistance, the internal voltage drop decreases, leaving more voltage available to measure in the closed test. That's why a closed reading might rise from 185 millivolts to around 240 millivolts in the example.